don't know where Oliver is. All right. Let's continue. So yesterday we were discussing bulk reconstruction. We discussed two different kinds of bulk reconstruction. So we had this global reconstruction where we had our bulk point little x, and then we represented it in the CFT as an operator with support on the set of points which are space-like separated from x. So this was the global reconstruction. And then we tried to shrink the boundary region that we would need to represent the point. And so we came up with this Rindler reconstruction, where now let me draw the picture from above. So the idea was that if we pick some boundary subregion A, then we define this AdS Rindler, or more generally causal wedge here, associated to it, where any operator which was inside of this wedge had a representation in the CFT which only used the operators in this spatial region. So if you like, you can think of the boundary Hilbert space as being a tensor product of the degrees of freedom here and the degrees of freedom here, like you would have in a spin system. And then the operators that we need to reconstruct this are the identity on this factor, and they're only non-trivial on this factor. Okay. So, and let me just again remind you that the algorithm that we used in both cases was that we solved the bulk equations of motion inward from the boundary using the extrapolate dictionary. It's the boundary conditions. So that's all well and good. It's still a little bit, on some sense it still may seem a little bit trivial, right? Because, we're just solving classical equations. So this is reconstruction, but it kind of, it doesn't really get maybe that deeply into how holography is working. So what I'm going to do now is I'm going to suggest a few paradoxical features of this reconstruction, and then try to explain how understanding better those features will lead us into a new perspective on how the correspondence is working, which is related to this idea of quantum error correction. And I'll explain quantum error correction when we get to it. So let me introduce a few puzzles or surprises or whatever you want to call them. So the first one is associated to radial locality. Right. So in quantum field theory, the most basic thing that you learn on day one of your quantum field theory class, or at least if you're taking a good quantum field theory class, is that operators commute at space-like separation, and that's essential to harmonize Lorentz invariance with quantum mechanics. Because if you had an operator here and an operator here, and they didn't commute, then by measuring this one, I could affect the outcome of what happens with this one, right? And so that's a telephone, right? Then I can send a bit that way. I choose to measure this or not, and then you do some experiment here, and now you get the message. So this commutativity at space-like separation, well, in the boundary CFT, it just manifests, right? Because the boundary theory is a quantum field theory, and so an operator here and an operator here are going to be commuting quantum operators, up to things like if it's fermions, they're anti-commuting. But let's talk about bosonic operators. Then it's an interesting question, right? So somehow the really funny feature of holography is that there's this extra radial direction, right? That's the thing where, probably the first time you heard about AdS CFT, somebody told you that quantum gravity in d+1 dimensions is equal to CFT in d dimensions. So you think, that's crazy, right? Where does this extra dimension come from? We have quantum gravity here, and I don't feel like I'm living in 5 dimensions. I feel like I'm living in 4 dimensions. Like I said it backwards, I guess. I don't feel like I'm living in 3 dimensions. I'm living in 4 dimensions. So where does this extra radial direction come from? right? That to me, that's sort of the big mystery of understanding how holography works. So we can formalize that question by looking at the algebra in the bulk. So let's consider a t equals 0 slice here, and let's consider a bulk operator, let's call it phi of 0, sitting here. And let's look at its algebra with some CFT local operator, O of x, sitting here at the edge of that time slice. So in the bulk, these guys are space-like separated. So given the rant that I just gave, you might think that they should be commuting quantum operators. Because otherwise, how can the bulk be local in the radial direction? And moreover, I can put this O of x wherever I want on the boundary. So it suggests that this phi of 0, right, that this should be true for all x, which are in this boundary time slice here, sigma. But from a quantum field theory point of view, this is very mysterious. Because when you learn quantum field theory class, the idea is that you start with some local degrees of freedom at the boundary, and then you make everything else out of the local degrees of freedom. So if you have an operator that commutes with all of the local degrees of freedom, then it has to be a trivial operator. So let me try and sharpen the intuition for that a little bit. So say that we have a spin system. Maybe we have some number of spins in a chain. So then the Hilbert space is a tensor product over the Hilbert space of each spin separately. So if there's spin 1/2, then each of these is a two-dimensional Hilbert space. So we just have Hilbert space 1, Hilbert space 2, so on, going down the line. So then it's a theorem about spins that any operator on the Hilbert space of the spin chain is a sum of tensor product operators, and in fact just a sum of tensor products of Pauli operators. So if you have, Pauli x here, Pauli y here, Pauli z here, right, operators like that. So any operator is a sum of things like, sigma x on the first site, sigma z on the 7th site, sigma y on the 4th site, etc. So operators that look like this are a complete basis of all the operators in the theory. So then if you have an operator which commutes with all of the single site Pauli operators, well, if it commutes with all of them, then it commutes with all of their products, and it commutes with all of their sums. So then it just commutes with everything, and so then it has to be the identity operator by Schur's lemma. So that seems to suggest, well, more than suggest, let's say seems to suggest that it's impossible to have an operator in the quantum field theory which is non-trivial, but which commutes with all of the local operators at the boundary. So that seems like a problem that holography is going to have to solve somehow, right? I mean, this is, if you like, this is kind of a sort of more rigorous formulation of this intuition that it's ridiculous for something in a lower number of dimensions to be equal to something in a higher number of dimensions. So for example, if the thing we had in the bulk here was quantum field theory, right? Say, I forgot about gravity and I came to you and I said to you, quantum field theory on the boundary is equal to quantum field theory in the bulk. I mean, this would be a proof that that can't happen, because then you really would need this equation to be true in the bulk, but then that would violate this sort of irreducibility of the local operator algebra.
I thought there are condensed matter physicists who call this bulk boundary. It's more like Chern-Simon.
Yeah. Right, so if the bulk theory is topological, that's a way out. So because then you wouldn't have this local operator here, that's right. So it has to be a non-topological bulk quantum field theory, absolutely. And in fact, this intuition, if you do something embarrassing, like you go and read Streeter and Whiteman, they'll talk about this here. And actually, although it's embarrassing, I recommend that you all at some point try and read Streeter and Whiteman. It's very educational, even though it's sort of outdated.
What is it?
What is Streeter and Whiteman? It's an axiomatic quantum field theory textbook called PCT, spin statistics, and all that. Yeah. And if you really want to know, what's the best argument for the CPT theorem or the spin statistics theorem, this is where you go to look. Yeah. And I mean, they're trying to be mathematically rigorous about quantum field theory, which, as you probably know, is a very difficult thing to be. So we often make fun of them because they never have any non-trivial examples. But nonetheless, they have axioms which we think should be true in quantum field theory, and they prove interesting things from the axioms. So, and in fact, I was a little bit mean. So in fact, some examples have actually been shown to exist. I think the most interesting one is phi to the fourth theory in 2 + 1 dimensions. Okay. So it's good to at least have some cultural knowledge of that field, even though it's not a mecca of contemporary research.
This could be the next big thing.
Right, and yeah, in fact, I should comment. So so if you've ever heard of Horacio Cassini from Argentina, so there's a slightly different version of being rigorous about quantum field theory. It's called algebraic quantum field theory, and we also like to make fun of them for similar reasons. But Horacio somehow has managed to learn just the important parts of that field and is doing many interesting things using the results, which sort of the rest of us are kind of mystified by. So I mean, I think this stuff, I suspect it may come back. Okay, anyway, but so if you look in that book, they tell you something which is called the time slice axiom. And what it says is that in relativistic quantum field theory, so these guys are very rigorous, right? So local operators don't exist; they're operator-valued distributions. So you have to. So if you want to talk about a local operator, you have to integrate it against a C-infinity test function of compact support. And that you should also know, actually. That's a true fact about quantum field theory. So this is called OF. And then the idea is that if you have a Cauchy slice of the CFT, sigma, here, and then you look in a neighborhood of sigma, then if you have a bounded operator on the Hilbert space that commutes with all the local operators that are smeared with their support inside of this neighborhood, then that bounded operator has to be proportional to the identity. So for them, that's an axiom of quantum field theory. Okay.
But the smeared local operator isn't a bounded union operator.
Well, that depends. No. Sorry, what I said was if you have a bounded operator that commutes with all of these. I didn't say these were bounded.
That's fine. But I'm
Yeah.
saying that if you just take a bulk operator and smear it over, it's not an example of a bounded union operator.
Yeah, that's true. So there are two ways you can deal with that. One is you can do something like you can take this and then you can do e to the minus that squared or something. Or the thing that they like to do is they say you take this operator and then you do its spectral decomposition and you take the projections that sit there. Okay. All right. So the time slice axiom seems to be in some tension with holography. Right, because holography says you do have this operator in the center, right? I mean, we're like that operator in the center, and well, at least to some good approximation, it seems like we commute with stuff at space-like separation, including in the radial direction. So somehow something's got to give here. Maybe I should comment that if you just say that this is true up to epsilon, that's good enough. You can show that to get it, for example, the difference between the largest and the smallest eigenvalue of the operator is bounded in some way by the epsilon that appears there. So this has to be violated order 1. Okay. Now, this puzzle can be illuminated further by using this Rindler reconstruction that we were talking about yesterday. So say we've got our phi of 0 here sitting in the center of the bulk. And say we've got over here our O of x that we think that we should commute with because we're space-like separated. Well, I can do something sneaky. I can say, OK, I'm going to find a boundary subregion A, which goes like this. So this bulk operator is clearly sitting inside this Rindler or causal wedge of A. And we can pick A to be a ball-shaped region, so we don't have to deal with the subtleties we were discussing at the end of the last lecture. And so then this operator has a representation in the CFT with support only here. Okay? But that means that all of its support is indeed space-like separated from O of x in the CFT. And in the CFT, we sure as hell have commutativity at space-like separation. So this implies that phi a of x of 0, this sort of representation with O of x is really 0, exactly 0. But then you could say, all right, well, okay, so maybe that was one local operator. But say now instead, okay, so we've still got our phi of 0 here, but now we want to think about this local operator over here. Well, that's okay. Now we can just send A this way. So A prime, and we have that phi A prime of 0 commutes exactly with O of x. And so you see, for whichever local operator you want, there is some representation that really exactly commutes with O of x. But as we discussed yesterday, I mean, these different representations, right, from the bulk point of view, they're just Bogoliubov transformations. We're just expanding the field in different bases, so they should all be the same operator. But then again, it seems like now we've constructed an operator that commutes with everything but is non-trivial. Let me see. I think I'll actually, let me draw here. So this actually, so this puzzle, somehow something funny is going on. And so we can, actually my favorite way of illustrating it, if I have phi of 0 here, is to split the boundary into 3 regions, A, B, and C. So now we can draw these Rindler wedges for A, B, and C like that. And you see that phi of 0 is not inside of the wedge for either A, B, or C. So in this setup, there does not exist a phi A, a phi B, or a phi C. So none of these regions has access to that operator, if you like. But the amazing thing is that any 2 of them do, right? So if we take the union of A and B, then now the wedge is defined here, going that way, right? But we could also do B and C, and then the wedge is like this, or A and C, and then the wedge is like this. So apparently there does exist a phi AB, a phi BC, or a phi AC. So where is the information? I mean, if we want to know, okay, I come to you with some state of the CFT, and maybe there's a spin in the center of the bulk. It's up or down. We want to know which. I mean, where is that information in the CFT? I mean, it's apparently not in A, not in B, not in C, but it is in A, B, BC, or AC. I mean, again, this is very puzzling from the point of view of quantum field theory, because from the point of view of quantum field theory, we think that the support of an operator is a well-defined thing. I come to you with an operator on the Hilbert space, and either it's supported in this region or it's supported on a different region. It's like in the spin system. You just know, right? I mean, either it commutes with everything outside the region or it doesn't. I mean, there's no funny business. So somehow AdS CFT is telling us that there's this kind of flexibility in how we represent the operators in the bulk in terms of the boundary degrees of freedom. So what I'm going to try and do in the rest of this talk is convince you that although this may at first seem surprising, it's actually quite natural. And there's an elegant way of thinking about how it works. Okay, any questions?
What about the gravitational dressing?
Yeah, very good. So if you want to think about the gravitational dressing, then you have to make sure that that the dressing of the operator also lies inside of the wedge. So in this particular instance, I can't quite make the argument the way I just said, because I have to pick a point on the boundary to send the dressing to. So then I only get sort of 2 of the redundancies, but not the third one. So for example, I get A, B, and BC. But it's still interesting because neither A nor B nor C has it, but A, B, and BC do. Yeah.
So you could have more than 3 regions also?
Yeah, absolutely. As many as you want. Yeah.
The minimum is
2. Well, I mean, 2 is also. Here 2 is also a little bit interesting here, right? You saw we got this kind of funny situation. But yeah, I think 3 really, 3 really brought it home to me. I mean, so this, Ahmed Almeri came to this, in Aspen one summer with this, and it was just, wow. That was the first thing I said. The second thing I said was, that's quantum error correction. which is what I'll try to convince you in a minute. Yes?
I have a little bit of confusion. So assuming about this commuting with all those operators, assuming they are all gamma matrices, and I can have gamma 5.
No, but we're talking about the Hilbert space, though, is a tensor product here, right? I mean, in the Dirac theory, you don't say that there's how shall I say? I mean, the gamma matrices by themselves don't act sort of irreducibly. Like, that's not all the operators. I mean, to generate all the operators, you need gamma 5 too.
Yeah. So
but there are certain. I mean, there are certainly. No, but. No. But nowhere did I say that. I mean, to be clear, this phi of 0 is not a local operator from the point of view of the CFT, right? I mean, it had support over a large spatial region. So you shouldn't just think of it as a product of operators, sort of site by site, right? I mean, it's made out of sums of products, and there are certainly sums of products of gamma matrices that don't commute with gamma 5. Okay. So far this sounds like a contradiction, but clearly that's not. I mean, AdS CFT is wrong is not the conclusion that's going to come out of these talks, right? So somehow we have to say a little bit better why, is that somehow this couldn't have quite done what we really expected, right? I mean, somehow. I think one of the key intuitions is that, well, these paradoxes about the algebras are true if we assume that these things that we wrote here really hold as operator equations on the Hilbert space of the CFT. But the Hilbert space of the CFT is a big and scary place. There are states in that Hilbert space where, there's a huge black hole sitting here, as Joanna was explaining, that, filling almost all of the space. And then, so what are we talking about with that point anyway in states like that? So I think the first people to really emphasize this are Papadodoudimis and Raju. They were thinking about the black hole interior, but never mind that. I think what they emphasized, very nicely, is that when you talk about trying to realize the algebra of bulk effective field theory in the CFT, it's probably safest to start by only trying to realize it within a subspace of the Hilbert space of the CFT. The subspace of states, for example, where the geometry doesn't look too different from the vacuum in this example. So what I'm going to now explain, for the next 45 minutes or so, is that this idea of having stuff only be true in a subspace is able to resolve all of these things in a very nice way, and that specifically these kind of locality puzzles, once you learn about quantum error correction, you'll see that quantum error correction just is a machine for generating these kinds of things. Okay. So let me now start by talking about quantum error correction. All right, so what is this quantum error correction? So quantum error correction is a thing which was invented by people who are trying to build, or, well, not themselves build, but thinking about building quantum computers. So with a quantum computer, the basic idea is that the memory, instead of being made out of bits, is made out of qubits. So you can think of, either way, you can think of the memory as a spin chain. But in a quantum computer, you're trying to keep track of the phase information and superpositions of the different states of the spin chain. You want to keep track of all of that. Whereas in a classical computer, you don't care if the phases get decohered. You just care about the sort of classical values of each of the spins. But it's very hard to preserve the quantum coherence of a large number of spins all at once. I guess some of the world experts at doing this kind of thing are here in Boulder, but it's not easy. The budget in Gila is high. And the reason why is because there's the environment out there, right? I mean, you can have your nice spin chain and it's in some nice superposition, and then a thermal photon from the window comes in through the window and hits it, and now suddenly your spin system is entangled with the radiation field in the room. And then the table that your computer is sitting on, a phonon can can come in through the table and bump into the sample, and now it's entangled with the phonons in the table, you know, and it's very hard to avoid these things. So it's very hard to maintain the coherence of your memory. So quantum error correction is a way of, you know, the idea. I mean, of course, you try to prevent this decoherence, but you say, okay, some amount of decoherence is inevitable. So instead, what we're going to try and do is figure out how we can recover from decoherence. How can we fix decoherence? So, I mean, classically, this is also potentially an issue, right? You know, like in cryptography, right? You know, you're trying to send a message, and you know, you want to, you know, make sure that if, you know, somebody steals one of the envelopes or something, that the message still gets through. So, and the basic idea, you know, in all of these cases is that you want to encode the message redundantly, right? You know, I mean, you know, also, for example, you're sending, you know, messages out to the Voyager spacecraft or something, you know, out past Pluto, right? Again, you know, it's very easy to lose some of the packets that you're sending. So the most obvious code, the one that you probably think of immediately, is called the repetition code. So say I want to send you a bit. Well, I could just send you one bit, but it might get lost. So, okay, no problem. Instead, I just send you 100 copies of the bit. That is what they do with Voyager. And then, you know, even if, you know, some of the bits get lost, or even worse, even if some of the bits get flipped, right, you can still look, right? So say I send you 100 bits, you know, say maybe you receive, you know, 90 of them. And of the 90 of them, 70 of them are up and 20 of them are down. Well, then you say, okay, well, probably, you know, it's more likely that 20 of them got flipped by accident than 70 of them got flipped by accident. So I'm going to assume that what you sent me was a 1 instead of a 0, say. Now, in quantum coding, however, this algorithm doesn't work. So can anyone guess why not? Yeah, that's right. It's because you can't make 100 copies of a qubit because of the no cloning theorem. So you need to do something more clever. And you know, I think for a while people thought because of the no cloning theorem it would just never be possible to do quantum error correction. You know, and even now one still meets skeptics. Although well, okay, anyway. But you know, it is kind of remarkable that you can do it despite the no cloning theorem. So let me say the slogan, and then we'll do an example, because otherwise it just gets too philosophical. So the slogan is, rather than repeating the information over and over, what you do is you encode the information redundantly in the structure of the entanglement between a larger number of degrees of freedom. So you know, if I want to send you 1 qubit, I instead send you 5. And then rather than, you know, having the 4th qubit being the one that contains the information, I send the information in the way that they're entangled. So let me now do an example, because I think otherwise that just sounds like some words. So this is my favorite example. I keep coming back to this example for the last 2 years. It's called the 3-qubit code. So the idea is now so a qubit is a 3-state qubit. So instead of 0 and 1, it's a 0, 1, and 2. It's just an accident of small numbers that the simplest example is qubits. But okay, we're doing qubits. So the idea is I encode one what's called logical qubit into 3 physical qubits. Okay, and I just have to state up front that 3 is appearing in 2 different unrelated contexts here. There are 3 physical qubits, and the qubit has 3 states. So there's nothing I can do about it. I'm sorry, but just try to stay on top of it. So the logical qubit, that's like the message I actually want to send, and then the physical qubits are like the atoms or whatever, the spin 1 atoms that I actually send to you, the actual stuff. And then from those you do some operation to recover the logical qubit that I actually want you to get. So let's think about how it works. So a state of 3 qubits well, it looks like this. So we sum I 0 to 2, Ci, I. All right. Any pure state of 3 qubits, of course, looks like that. But rather than sending you that, because I just send you the 1 qubit, who knows, maybe it falls in the ocean or whatever. So instead, I'm going to send you 3 qubits, which are in a state which looks like this. Doesn't look very different. But the idea is that I tilde here is a basis of a 3-dimensional subspace of the 27-dimensional Hilbert space of 3 qubits. So maybe I'll write it here. So let me tell you explicitly what subspace we're going to use. So the encoded or logical 0 state looks like that. This is sometimes called a GHZ state. So just in case you haven't heard of it before, this is what a GHZ state is. The encoded 1 is 0, 1, 2 plus 1, 2, 0 plus 2, 0, 1. And the encoded 2 state, 0, 2, 1 plus 1, 0, 2. Okay, can anyone guess what the last one is? Huh? Yeah, 2, 1, 0. Good. That's the pattern recognition. Yeah. Okay. So now let's just make a few comments about this subspace, and then we'll try to understand why we picked this subspace. So first of all of these states are very entangled. Right? None of these states are close to being product between the different physical qubits. Okay. Secondly, and let me just emphasize this again, there are 2 different 3s here. In fact, now there are 3 different 3s. There's the 3 states of the individual qubits. There's the 3 states that are the basis for the code subspace. Those 2 3s have to be the same because we're sending. Well, sorry, I mean not even really, right? So there's a logical qubit which is these 3. There are physical qubits which also happen to each have 3 degrees of freedom. And then finally, there are 3 of the physical qubits. Okay, but if you get confused, just look at this equation, and hopefully everything will be clear.
Aren't you just adding 3 spin 1s to spin 1?
Oh, you're asking, is this the singlet? I think it's not, right? Yeah.
1 plus 1 plus 1 is 1.
Yeah, I think you can think about it that way. Yeah. Yeah, in fact, there's a general machine of constructing these using group theory, but yeah, that's too fancy for these lectures, I think. So I'm just going to present it as I just happened to write this one down. Okay, so it's very entangled. It's also symmetric between the 3 qubits. It's not completely symmetric, but it's symmetric under cyclic permutations of the qubits. And that's going to be convenient for our future analysis, so that it decreases the number of cases we have to consider. Okay, so now why did I pick this subspace instead of a different one? So here's the big claim. The claim is that there exists a unitary operator, U12, which acts on the Hilbert space of the first 2 qubits, which has the property such that if this encoded state I tilde is equal to U12 tensor the identity on 3, acting on a state which looks like this. So it'll be I on the first qubit, tensor product chi on the second 2, where this chi is a maximally mixed state 0, 0 plus 1, 1 plus 2, 2. All right, so it's not obvious that there's a U12 like this, but I claim there is. I won't write it down for you just because writing down 9 by 9 matrices on the board is not a lot of fun. But you can entertain yourself figuring out what U12 has to be. It's uniquely determined by this, actually. Okay, so why do we like that? Well, Okay, so say I have my qtrit in Cambridge, and I want to send it to you here in Boulder. Well, what I can do is, okay, the first thing I do is I prepare my 3 physical qtrits in this state. Okay, and then I send that state to you in Boulder. But you know, somewhere in the middle, I don't know, in Nebraska or something, say the 3rd qtrit, you know, falls out of the airplane or something. So then you only get the first 2 qtrits in Boulder. Well, that's okay. You can just walk over to Jilla, where they have quantum computers, or soon will, and act on your 2 qtrits with U12 dagger. And when you do that, you'll just get back psi on the first qtrit. Well, and you won't have the 3rd one, so you'll get some mixed state on 2, but who cares? Because, hey, look, you have psi on the first qtrit. And then the truly amazing thing is that, well, because of the cyclic symmetry, if this is true for 1 and 2, it's also true for 2 and 3 or 1 and 3. So this means that given any 2 of the qtrits, access to any 2 of the qtrits, you can recover the state that I was trying to send you. So if you like, you can correct for the erasure of any one of the 3 qtrits. So that should already sound kind of familiar, right? Because that's kind of like what we had going on here, right? Like we had this operator in the center of the bulk, and well, we couldn't get it from any 1, but we could get it from any 2. And by the way, incidentally, it should be clear here that you can't get it from any 1, because if you could get it from 1 and you could get it from the other 2, that would be cloning. Okay, so being able to get it from 2 means you can't get it from the other 1. And so that's the same thing, or it sounds similar to what was happening here. Okay, it's not quite the same, though, as what was happening here, because here I was talking about operators, and here I'm talking about states. But actually, it is the same, so let me now rephrase this in terms of the operators. So say we have some operator. So say that O is just some qtrit operator, so that acting on the state I, it just multiplies it by some matrix, arbitrary matrix, O, arbitrary 3x3 matrix. So then we can certainly lift this to if you like, a logical O operator that acting on this code subspace acts with the same matrix elements, Ji, J tilde. But this lift will not be unique, right? Because here we define, this operator is only defined by its action on a 3-dimensional subspace of the 27-dimensional Hilbert space. And so in principle, there are various ways that this O tilde could be defined on the orthogonal complement of the code subspace. Okay, and this is called the code subspace, by the way. But there's no guarantee a priori, if we just pick some stupid subspace, that I'll be able to find an O tilde which has support only on 2 of the physical qtrits. In general, for just a generic subspace, you'd probably think that this O tilde, in order for it to act the way we want on the subspace, it would have to use all 3 of the physical qtrits, polys on all 3 of the physical qtrits in some non-trivial way. But actually, that's not the case here. So the reason is, careful, it's a death trap. So the reason is because we can just define something clever. So I can define, for example, an operator O12 in the following way. So I act with U12 dagger to decode the code subspace. Then, while the code subspace is decoded, I just act on the first qtrit with an operator which is just literally these matrix elements here. Okay, just the actual matrix elements of the operator. And then once I'm done, then I re-encode with U12. And now look, all the operators I wrote have supports only on the first 2 qtrits. And so similarly, there's also a O23 and an O13. So now you see that any operator whatsoever, any logical operator, acting within the code subspace can be represented on any two of the qubits. Okay, and that's really starting to smell like what we had here. So yeah, maybe I should write explicitly, right? So this O12, what it does is, if I act on any state in the code subspace, it's the same as acting with this O tilde, and in fact the same is true for the Hermitian conjugate. Moreover, so that was sort of like our sort of third puzzle there. Yeah, go ahead.
So for O23 and O13, do you need unitaries like U23?
Yeah, that's right. That's right. Yeah, but those are but by the symmetry, those are guaranteed to exist if U12 exists. That's right. Yeah. Yeah, and there's a little bit of freedom here too, also, because I could, for example, I could have chose to put the message onto the second qubit instead of the first qubit. So that was just arbitrary choice. Okay. So this is kind of like the third puzzle. Moreover, we can also get something that's kind of like the first puzzle. But before I say that, let me now try to make the dictionary between this and what was happening there more explicit. So I want to view this qubit code as an example of holography. So let's see how the dictionary works. So first, let me draw the picture. So here's 1, 2, and 3. So the three physical qubits correspond to the local CFT degrees of freedom. So this is a very simple CFT. It's a lattice CFT. That doesn't really make sense. So it's just a lattice QFT. But it's a lattice QFT with 3 lattice sites. What could be simpler? Well, what could be simpler is that there's only one logical qubit. And that corresponds to the local bulk effective field theory degrees of freedom. So our bulk theory is even simpler. There's only one lattice site sitting here. So then if we draw these Rindler type wedges, right, what we seem to have discovered is that this guy is not in the wedge for any one of the boundary subregions, here just being the individual physical qubits, but it is in the wedge for any 2 of them. Okay? And we'll keep coming back to this model over and over again because it contains surprisingly, avatars of surprisingly many features of AdS CFT, at least for me. Well, it's not surprising anymore because I've been saying it for 2 years, but it was surprising. So to emphasize that, let's now get back to our first paradox, right, where we wanted to commute with all the local operators at the boundary. So let's look at the commutator. So let's consider. So let's say phi tilde and psi tilde are 2 states in the code subspace, just two arbitrary states, but in that 3-dimensional subspace. Then we can look at, so we can take O tilde to just be some logical operator, so if you like, some bulk field sitting here, right? And so depending which O tilde you pick, it might be phi, it might be phi dot, who knows, but some O tilde. And then let's compute its commutator with an arbitrary operator which acts only on the 3rd qubit, right? So an operator that acts on only one of the qubits is a local operator in the boundary, right? So by space-like commutativity at space-like separation in the bulk, we had argued that we want this to be 0. And, well, it is 0 because this guy is always acting either to the left or to the right on something in the code subspace. So I can replace this by O12, and now indeed these are now just acting on different physical qubits, and so this is 0. And similarly, had I put some operator on the first or second qubit here, I just could have picked O23 or O13, and I would have still concluded that the commutator was 0. So within the code subspace, we can easily arrange to have a non-trivial operator that commutes with all of the local operators at the boundary. Okay. So So this model indeed has locality in the radial direction.
It doesn't compute with operators like Harlow.
What? No, it doesn't. No, but it can't, right? Because, for example, I could represent phi here and also phi dot here, and then I want them to not commute, right? I mean, the bulk algebra is non-abelian, so I want to get a non-abelian algebra, but I want it to be consistent with locality.
How
Yeah.
does it work if you want to fill in more bulk points? You would think that the number of bulk points grows faster than the number of bulk.
Yeah, good. I mean, we'll discuss that in a lot of detail. So, yeah, great question. But yeah, just hold on a sec. Any other questions about this? Yeah.
So it's probably obvious. Why are you working with a three-dimensional Hilbert space? Is it because 1 plus 1 plus 1 has 1 as one of its, you're adding any whereas spinning halves doesn't give you two states?
Yeah, I think there should be a way of saying it that way. The only way I can say it is there's this question of whether or not codes exist is a sort of delicate question. Like, so if we just, say for example, instead of qtrits, I tried to do qubits, and I tried to make a code, it wouldn't work. So, it's just, so the easiest code that involves qubits encodes 1 qubit into 5 qubits. And then 5 is bigger than 3, so it would have been too much writing to discuss here. Yeah, so I think there should be some group theory way of understanding that, but
I'm just trying to add angular momentum in my head.
yeah, I think if you do it correctly, you'll get the right answer. I can't do it correctly off the top of my head. Yeah.
So you have a product space of 3 identical Hilbert spaces.
Yeah.
Label them 1, 2, 3.
Yeah.
But do you have a way to actually distinguish which one of the qubits which was blocked to which Hilbert space it is dependent?
So there are too many. Which qtrits are you talking about? I mean.
So you have message encoded in this 3.
Yeah.
physical.
Oh, you mean how do I know which one got lost?
That's right.
Yeah, that's a great question. Great. So yeah, so in quantum error correction, there are different kinds of errors that you can try to correct for. So the errors I'm discussing here are called erasures, and the defining feature of erasures is that you know which ones got erased. So for example, when I sent the 3 qtrits to you in the mail, I put letters onto the envelopes, and then you just look at the outside of the envelope and it tells you which ones you got. Yeah, indeed. So when you're doing a quantum computer, you're interested also in more general kinds of errors where you don't necessarily know what got erased or something, instead of getting erased, it got hit by a hammer and so on. And the interesting thing is that codes that can correct for erasures usually end up being good enough at correcting other kinds of errors too, maybe slightly less efficiently. Yeah, I mean, we could give a whole lecture about that, but for AdS CFT so far, erasures seem to be the errors that are most naturally motivated because you know which region of the boundary you have access to. All right. So let me just make a few comments here. All right. So the first comment is that the entanglement in this state chi was essential for this to work. So say in this equation that instead of an entangled state, we had a product state here. Say 0, 2 times 0, 3. Well, on 1 and 2, you're still going to be able to do the correction because it doesn't matter what chi is here. But if that were true, then what it would mean is that 3 was just irrelevant for the message, right? It would mean that even after the encoding, 3 was just sitting in a product state out here all by itself. So it can't possibly contain any information about the encoded message. So that entanglement, that's sort of maybe a sharper way of seeing what I said earlier, right? It's really the entanglement that makes it possible to have this redundancy. Maybe another way of saying that is, I mean, here we have a situation where if you just have 1 by itself, you don't have the message. But then if I additionally give you 3, you do have the message, right? And there's no way to have that if 3 is just sitting here in some pure state same state everywhere in the code subspace. Okay, so that's one comment, is that chi entanglement is important. Okay. A second comment is that, you might say, okay, I told you about the bulk interpretation of three-dimensional subspace of the CFT. But I mean, come on, what about the rest of the Hilbert space? You told me this is an isomorphism of Hilbert spaces. I mean, come on, you didn't tell me that, you know, AdS is contained in CFT. You told me that AdS is equal to CFT. So what about the other 24 states anyways? So here I'm just going to make a claim, which in the context of this model maybe is, you don't necessarily have to believe me, but then in the more general models we'll discuss in a moment, it should be more clear that it's a correct claim. The claim is that the orthogonal complement of the code subspace correspond to black hole microstates. So the idea is that in the rest of the code subspace, we can draw a picture here. So here are 3 qubits, 1, 2, and 3. And in the rest of the code subspace, there's just some big black hole sitting here, and it ate our bulk point. And so we're just left with the microstate degrees of freedom of that black hole. And as you see, there are a lot more microstate degrees of freedom of that black hole than there were in the effective field theory that would have been there if the black hole wasn't there. Okay. And that's sort of consistent with this general idea that sort of most states should be black holes in quantum gravity, right, as Joanna was saying. Well, so remember, most states in the CFT have high energy, right? So this is a model for the CFT. So if you like, the code subspace is like the low energy states in the CFT, and then the orthogonal complement of the code subspace is like the rest of the states, the high energy states. And those are the ones where there's a big black hole sitting here. I mean, here it's a 27-dimensional Hilbert space, so okay, I mean, what does it mean for it to be a black hole? But you know, hopefully I'll convince you soon that it's reasonable to think of it that way. Yes?
So when you say big black hole, you've expected sufficiently high energy states that really no local structure to speak of. So you mean in the sense that the whole, you know, just like one big black hole?
Well, yeah, again, here it's a little bit hard to talk about how big the black hole is, because there was only one point in the bulk to begin with. So either it's in the black hole or it's not. So when we get to the tensor networks in a bit, I think it'll be more clear. Yeah?
In this 3 qubit case, there are states outside the code space where I just change, say, take 2 tilde, and
Yeah.
qubit.
Yeah, yeah.
The first 2 could still reconstruct the qubit that was allegedly in the black hole.
No, not necessarily, because there are other ways of preparing that state where you give it a different interpretation. Yeah. No, let me not go through that in detail. Ask me later. But yeah, I know this confusion, and yeah. You want each state to have a unique physical interpretation. If you start trying to play that game, you're going to get confused. Okay. So let me just now make another general comment. So there's a general theory of when the analog of this U12 exists, right? I mean, this is just some example, who cares, right? So, you know, if this weren't a general phenomenon, well, I wouldn't be telling you about it, but okay, it is a general phenomenon, and there are general theorems about, you know, under what conditions can this U exist. So let me just tell you one of the conditions. I think I don't have time to try and derive it for you. So say we have n physical, and I'll call them qubits. So a qubit is a d-state qubit. So a qubit has d equals 3, and a qubit has d equals 2. I don't make up these names, okay? Say we have k logical qubits. And then finally say that we want to be able to correct for L erased qubits. Okay. Then there's a necessary and typically sufficient condition to be able to do it, which is that you need n to be greater than or equal to k plus 2L. So hopefully the sign of everything is clear, right? It's saying if you want to send a bigger message, or you want to be able to protect against more erasures, you need more physical qubits, right? That makes sense, right? You need more redundancy if you want to send more stuff and protect against more stuff. So we can check. So in our qubit example, right? So we had n equals 3, and we had k equals 1, and we had L equals 1. And well, I guess we can check that 1 plus 2 is 3. So this one is saturating the condition, which is good. Yeah.
So this doesn't depend on D.
What? No, it does not depend on D.
Why would you do a 3-qubit code?
No, I said it was necessary, and I said it was typically sufficient. But let's understand what typically sufficient means if you choose a random subspace. But in order for the error to be down, you need the Hilbert space to be big. So you view it. It's a necessary, and then when things are big, sufficient condition. But the errors, for a random code subspace. Yeah, AdS CFT is not a random code subspace, so I don't want to put too much into that. But let's just emphasize it's a necessary condition. Okay, so now let me just make two general comments about the kind of code that AdS CFT is. Okay, so the first comment has to do with how the information is encoded. Structure of AdS CFT code. The first comment is that the radial direction basically is the same thing as the quality of protection. So say I have some bulk degrees of freedom, some bulk operator sitting here, okay? And I at the boundary want to somehow screw up that operator. I want to flip one of its eigenvalues or something. Well, by using the Rindler reconstruction, you see that I can represent this operator just on this tiny little region here, which means that by doing things in the CFT which don't require very much non-locality, I can affect this thing. And in particular, if I just erase this degree of freedom, I no longer have access to it. I just have access to this whole huge thing here. I still can't recover that operator. So this is a badly protected operator. It's sort of too local with respect to the physical degrees of freedom in the CFT. But then as I move the operator in, so say I go to put it in the center, you see I actually need a quite large erasure to take away the knowledge of that operator. So for example, even this huge erasure here still can't affect that operator. In order to erase it, I need to take away more than half of the boundary. Or said in the other way, I need more than half of the boundary if I want to recover this. I can, to have access to this. Anything which is less than it is going to commute with it. So this is a kind of new and sort of, I would say, quantitative interpretation of what this radial direction in holography means. It means how well protected the information is from the point of view of, a daemon who can act on the boundary, or an environment, if you like, who can act locally on the boundary.
This is AdS space. Every point is the same.
No. But I've chosen a conformal frame here. So when I talk about large and small on the boundary, I have a round metric on the sphere here, and then I've broken that. That's fixed. Yeah. By doing conformal transformations, I can take small and make it look big. Yeah, that's right. Yeah.
So 5 years ago, people were talking about AdS era and how deep into the vault was going to be right, where you're more close range.
Yeah.
Isn't that also?
Yeah, so this is a sharper I mean, it's not just 5 years ago. I mean, 20 years ago, people were saying that the radial direction is like scale in the boundary theory. And this is certainly consistent with that. The difference with this is that this is an equation, right? It tells you, you ask a sharp question. How big of a boundary region do I need to access this? That's a question whose answer is a real number. Okay. Whereas this, the traditional way of saying it, there was some sort of hand waving about how, inside is the IR and out near the boundary is the UV. Okay. So that's one comment. The second comment I want to make is about black holes. Well, not just about black holes. So, okay, so, let me just call it holography. So let's try to see how this works in practice. So what I'm going to do is I'm going to use this inequality that I wrote over here and try to apply it to AdS CFT and see what it tells us, and then see whether or not it's surprising what it tells us. Okay? So to be very concrete, I have to pick a code subspace. Right? I have to pick a K. So what I'm going to do is I'll take a region in the center whose size is of order the AdS radius. And then the rule will be that to make the code subspace, I'm allowed to act on the ground state with K operators, with K bulk operators inside of this region. Okay? And so act or not, say. And so that gives a subspace which grows exponentially in K, whose dimensionality grows exponentially in K. And now the question is, how big of a boundary region do I need to access that? Okay? Well, to answer that, I also have to tell you what is n. What's the number of physical degrees of freedom in the CFT? And that's a little bit uncomfortable because, of course, it's a continuum quantum field theory, so it has infinitely many degrees of freedom, right? If we take the lattice spacing to 0 on the boundary. But most of those degrees of freedom are totally irrelevant for our purposes because they're deep in the UV and they only affect what's going on very near the boundary. So one way of saying that more precisely is that for things that are in the center, this smearing function that I wrote down before, this K, varies smoothly over the scale of the horizon. So it can't pick up, subtle, very UV information in the CFT. So in fact, in a large N theory, the only thing it's really sensitive to, say in n equals 4 super Yang Mills, is if you like the matrix degrees of freedom, or more generally, this will be what I called alpha. In the CFT. So the sort of the zero modes of the CFT are basic, maybe the first 1,000 spherical harmonics or something, but nothing that grows with n from the point of view of the boundary. So we can just think of this little n as being order capital N squared. So now first let's consider the case where K is order 1. So we have a small code subspace. We just act with a few operators, nothing too fancy. So then what that inequality tells us is that L, the erasure, has to be less than or equal to n over 2. So it says that we can erase at most half of the degrees of freedom, but not more. But actually, that's what the AdS Rindler reconstruction tells us too, right? Because this stuff is in the center. So up to some order 1 factors, which we're not being totally careful about here, you see that having more than half is enough to reconstruct what's going on here. So that's good. This sort of information theoretic inequality is consistent with the AdS Rindler reconstruction. But now let's start cranking up K. So what happens if we make K bigger? Well, for a while nothing happens because n squared is pretty big. So when you look at this inequality, it's still going to be dominated by the n squared on the left-hand side. So indeed, nothing is going to change until K becomes of order n squared. But when K becomes of order n squared, well, then we're acting with a number of local operators here, which is comparable to the entropy of a black hole occupying that region. So then from the bulk point of view, we think, well, maybe it's okay if we start actually losing access to this information. So again, this inequality, which by the way is called the quantum singleton bound, I don't know why, but that's what it's called. According to the quantum singleton bound, right when you're sort of no longer going to be able to reconstruct this, then the bulk says, well, that's okay, I put a black hole there. So let me say this again more poetically. So the CFT comes to you, and it says, okay, you think I'm a d-dimensional CFT, but really I'm a d+1 dimensional theory of quantum gravity. And you say, that's crazy. So then the CFT says, okay, try me. So fine. So you take the CFT and you start acting with operators in the center and trying to reconstruct bulk effective field theory. And you're doing this for a while and you're thinking, wow, this CFT is pretty clever. Actually, it kind of does look like it's living in d+1 dimensions. How's that happening? And then you say, okay, well, you know, I'm a smart guy. I know about the quantum singleton bound, so I'm gonna catch you by acting with enough things here that there's just no way that you can continue pretending to be a d+1 dimensional theory. All right. And you know, the CFT is kind of looking at me smirking, and so I do it, and then finally it says, you know, right when I get to the point where, you know, I'm going to catch it and it can't hide anymore, then it says, oh no. I forgot to tell you, I'm a gravitational theory in the bulk, and I made a black hole. So it's really the black hole, you know. So you know, and it's the black hole that saves it, right? So the black holes, I would say, are really essential for the functioning of holography, and we already saw some of that earlier because we saw the free energy at high temperature sort of was scaled like the area instead of like the volume in the bulk. So I mean, it's not a surprise, this conclusion, but this here, it's really sort of staring you in the face. And you know, since this is a school, maybe I want to emphasize. So when people talk about why quantum gravity is hard, there are various things that people say. Most of them are wrong. Okay. One thing you sometimes hear is that there's diffeomorphism in the bulk, invariance in the bulk, so local operators don't make sense. Okay, but that's true in the string worldsheet too, right? In 1+1 dimensions, you can write down the Polyakov formulas, and there's a dynamical metric. There's a Lagrangian. Everything is, you know, more or less the same. It's true you have to be careful about gauge invariance, but not any more careful than you had to be in QED. Okay, so diffeomorphism invariance, no problem. Another thing people say is, well, quantum gravity is going to be hard because it's non-renormalizable. And you know, there are people who are working very hard, for example, to decide whether n=8 supergravity is renormalizable in 4 dimensions or not. Okay. Pions are not renormalizable. That's okay. The Fermi theory is not renormalizable. That's also okay, right? Being non-renormalizable, it doesn't mean that you're not going to end up being described by quantum field theory, you know, which is something that we understand very well. The thing about gravity, which is special, you know, the only reason that gravity is different is because there are black holes. And in fact, you know, when there are theories of gravity that don't have black holes, like the string worldsheet, they're not mysterious. You can study them using local Lagrangians. Okay. So if there's anything you take away from this lecture series, I hope it's that. All right. Let's see. How are we doing on time? So we have like 5 minutes or something? Or let's do questions first, actually. Yeah. 8 minutes? Okay. Yeah.
What does that have to say about black hole evaporation and like the areas decreasing?
Yeah, so black hole evaporation is a sort of subtle question from the point of view of AdS CFT, because the black holes that evaporate are atypical states. You know, the big black holes don't evaporate, they just sit there. So to get a black hole that evaporates, you have to go to lower energies, where most of the states just correspond to a gas of photons and gravitons and whatever. And then you need to just prepare one of the special ones where temporarily it looks like a black hole. And if you do that, then if you evolve for a while, eventually it becomes more typical and it evaporates. But this level of subtlety, right, is not something that using these methods so far we're able to address. Because, I mean, this is fairly crude, right? I mean, the only weapon I have here is locality on the boundary CFT and commutativity at space-like separation. Yeah, no, eventually, of course, we do need to be able to understand that better. Yeah. Yeah.
Let's say you want to send k=1 logical qubits.
Yeah.
But you arrange for a system that actually has k=100 logical ones, and arrange them geometrically in a symmetric fashion so that you only need to recover one of them. Then all of a sudden you're back to the classical system where you send redundant information.
Well, okay. Maybe let me make a comment on that. So. It's very important here that I want the recovery procedure to not depend on the state. So, and that's really where no cloning, I mean, there's no problem with cloning some particular state. Another way of saying it is you can clone in a basis. I can certainly write down a unitary that sends 0 times I to I times I, right? That's certainly a unitary transformation. What's not a unitary transformation is to have it work for an arbitrary state times 0 go to an arbitrary state times the same arbitrary state. So I think if you think carefully about what you said, you'll see that either you're cloning in a basis or it's not possible. Okay. So the next thing I was going to do, which I think I probably won't have time to do in detail, but I'll maybe start so that we can get into it faster tomorrow, is I'll give a sort of more interesting example of this, right? Because it's a long way from one point in the bulk to actual Lorentz invariant bulk effective field theory with gravity. Well, I can't quite get all the way there, but I can at least give you an example which is still exactly soluble, but which has a volume's worth of degrees of freedom in the bulk. Okay, and if I can't even do that, I mean, come on, what are we doing, right? So let me start telling you about the structure of that, and then we'll continue tomorrow. And hopefully we'll get to the Rutak-Yanagi formula also tomorrow, although we'll see.
Paradox.
Yeah.
Is that just because your bulk reconstruction is state dependent, so that if you're just thinking about gravity coming to the full absolute state, it will not be?
Well, I don't call it state dependent. State dependent is a term which is used for something else, which is a violation of quantum mechanics. So the correct way of saying it is that the mistake in the beginning was I asked for the bulk effective field theory algebra to hold in the entire Hilbert space, and I shouldn't have done that. There's really only a subspace of the states where it needs to hold. And exactly which subspace you want depends sort of on which question you're interested in. So I'm giving you the simplest version where we just study excitations of the vacuum. But you can do things like including black holes in the code subspace and trying to reconstruct what's outside the black holes, and that more or less works. But I just want to give you the simple version here. But there's that term is used to refer to nonlinear measurement theory, and I'm definitely not doing that. Okay, so let's see. Yeah, so let me just say a little bit about how these models work. The idea is that now, instead of having the CFT be 3 qubits, we're going to have it be n qubits. Now we're back to qubits. And then the bulk effective field theory is going to correspond to, and if you like, these are physical qubits, corresponds to k logical qubits. So if you like, I'm going to give you a 2 to the k dimensional subspace of the Hilbert space of the 2 to the n dimensional Hilbert space of n qubits. And we're going to interpret that as the subspace where bulk effective field theory happens. Roughly speaking, like I said before, you should think of this subspace as being like the low energy states in the CFT. Now, actually, that's not quite right. What it really is it's the image under the conformal group of the low energy subspace. So to give you something that respects the AdS symmetry better. Now, there are various ways that I could try to describe to you which subspace I'm interested in. The sort of very fundamental way of describing it to you is to just give you the wave function of each state in the subspace. That's what I did over there, right? So, given a complete basis of the physical qubits, I want to give you, the components of some basis of the code subspace, right? So here, since there are k logical qubits, there are k of these, and then I give you their matrix elements here. So this is the analog of these 3 equations here. And so let's give this a name. Let's say that let's observe that we can interpret this as a tensor, I1 to the IN, J1, JK. So this is a tensor with n plus k indices. Each one runs from 0 to 1. So then to give you this subspace, all I need to do is I need to give you that tensor. And so the way I'm going to give you that tensor is by using what's called a tensor network. It would be too hard for me to just write it out for you on the board like this, because I'm going to take n to go to infinity, so I have to do it in at least a somewhat more efficient way. So I'm not going to tell you what the tensor network is today. I'll tell you tomorrow. But let me just close by saying a little bit about tensor networks so that you get some of the philosophy. So the idea of a tensor network is that you start with a small number with tensors with a small number of indices, like say 4. So this here, by this picture, I mean, if you like, some tensor with I1, I2, I3, I4. And then maybe and then I draw several of these tensors. They don't all have to be the same. So maybe this one has 5 indices. Maybe this one has 3 indices. And then the idea is that for each tensor I draw, let's call this one t hat, and let's call this one t tilde. The idea is that now I'm allowed to connect some of these lines. So, for example, I could connect this one. I could connect this one. I could connect that one. Maybe I could do that. And then each time I connect 2 of the lines, what it means is that I contracted the indices together. So, for example, this guy had 4 indices. So, for example, we could interpret this as contracting the first index here with the first index there. And then this guy, well, I guess I contracted 2 of his indices together like that. And maybe there was a k here, and that goes to a k here. And I don't know. I guess what did I do? There's also a I2 here, maybe from this one. And then this guy has 3 free indices. And this guy has 1 free index. I don't know. Let's call it L here. Here I constructed, well, here it's kind of silly. I guess I decreased the number of indices because I ended up with only 3 free indices. But you see that depending on how I contract these things, I can start with small building block tensors, and I can gradually produce tensors with huge number of indices just by drawing the picture and by telling you what each of the individual tensors is. Let me close by just saying philosophically, this, it just seems like some trick, but in the last 5 or 10 years, this has proved to be an incredibly powerful method of generating candidate wave functions in Hilbert space. Especially in condensed matter physics and in quantum information theory, people are using these methods to study things like the Ising model in a transverse field, and computing scaling dimensions, which are almost competitive with Monte Carlo. And the reason why this is so powerful is because Hilbert space is as we said, it's a very big and scary place, right? I mean, if you have 30 qubits, right, you have 2 to the 30 states, and so if you think about, you have a basis of 2 to the 30 states. And then the number of distinguishable quantum states you have is e to the 2 to the 30. So the number of possible configurations is enormous. But most of those are just completely uninteresting from the point of view of physics. So what tensor networks are good at doing is sort of focusing in on a small piece of the Hilbert space that somehow cares about the local structure of the Hilbert space, the tensor product structure into the individual pieces. And for systems where the Hamiltonian is local with respect to that tensor factorization, it seems like it focuses in on the right subspace of the states. And so we'll see tomorrow I'll be able to construct for you a tensor network where it produces a generalization of this code where we can see all of the same things continue to be true. And then we'll go to Rutakunagi from there. All right, thanks.
One or two questions.
For me, what's the role of CFT in the model, especially large and large gap? And does that come, how should I think about it? Like, your model is, even if I say that it's CFT, I can't see exactly where the code is.
Yeah, that's right. So that's related to the fact that this is a toy model, right? So those conditions we saw were sufficient to get the real deal in the bulk. Einstein-Hilbert action, local particle physics Lagrangian. Here we're not trying to get all of that, right? Because if we tried to get all of that, we would just be back to the CFT. So the question is, which aspects of the correspondence are we trying to model? So the n you can think of, if you like, as the number, here in the Q-trit model it was 3. Now unfortunately there were these 3 3s, but here it's the 3 of the Q-trits. It's the number of degrees of freedom at each physical site. So we'll see tomorrow in the model that the entropy of the black hole scales with that. Okay, so that is more or less analogous to n. And in general in the tensor network model, so that's the range of these indices, and it's good to want that to be large. So for example, the Stanford group, by choosing the tensors to be random, has shown many beautiful things. Hold in the limit where these guys are large. So that's large n. Large n has a nice avatar here. Large lambda, or if you like this gap, is a thing which, so far as I can tell, does not have a simple analog here. I mean, I think this is not sort of strong enough to capture that. Roughly speaking, the reason is because large lambda, somehow it has to do with the interactions that go on sort of within each Q-trait at the boundary. And so far we're just basically using spatial locality at the boundary. We're not using the fact that, it's actually n by n matrices or something.
So as far as you're concerned about emergent, local, radial direction, can I say your toy models can be more general compared to AdS, CFT?
Yeah, well, so what it's capturing is locality at the AdS scale. Right, so all the pictures I've been drawing, right, and you'll see more clearly with the tensor networks that we're going to get locality at the AdS scale. And that does not require a large gap. So for example, these higher spin theories are also local at the AdS scale, and so is the SYK model. So I'm not alone in writing down models that neglect locality at below the AdS scale. It's embarrassing that we all keep doing it, but somehow it seems, at least we think we're learning things from it. But sooner or later we are going to have to cross that river. Yeah.
Tensor networks were most powerful with low dimensions.
Well, yeah, both of those statements are definitely true. So matrix product states, for example, are tensor networks that are supposed to reproduce the ground state of gap systems. In one dimension, that's right. Yeah, so Mira, so the things I'll draw tomorrow are somewhat similar to Mira. I think they're better than Mira, but they're somewhat similar. And so Mira is designed to reproduce the ground state of a scale invariant system. And so are these. But it's still going to be in one spatial dimension. Going to higher spatial dimensions is in principle possible, but you see, it depends what your goal is. So if your goal is actually, to compute scaling dimensions, of actual stuff for a real local Hamiltonian, it gets much harder as you go to higher dimensions. But, I'm not actually trying to make a controlled approximation to n equals 4 out of this. I'm just trying to give a cartoon or a skeleton of how holography works. And at that level, there's no problem with extending to higher dimensions. The pictures get harder to draw, but okay.
Maybe one more question.
Yeah, over here, maybe? Or?
So it seems like a lot of the structure depends upon the time-like periodicity that's being assumed.
What time-like periodicity? What? Wait, sorry, what time-like periodicity? No, not here. Not in this discussion. You mean yesterday? Well, no, that wasn't a thing that was assumed, though. That was a thing that I got by solving the scalar wave equation in the bulks. I'm sorry, you mean the you mean the boundary conditions at infinity? I mean, yeah, it's true that followed from the boundary conditions, but that's not why I chose those boundary conditions. Yeah, I picked it because I wanted a unitary theory in the bulk.
Right, which applies, but it still applies.
Well, no, you have to be careful, right? Because it's not really time-like periodicity because there are these deltas, right? So the frequencies were really delta plus 2n plus L. And this delta is in general irrational numbers. And they're different, different operators have different deltas that aren't commensurate. So the correlation functions of the conformal field theory are definitely not periodic in time.
I thought it ended up being that way for like 10 examples.
I'm not actually sure. Do you guys know about that? I thought
maybe you should truncate only to gravity.
Yeah, maybe if you only look at the chiral BPS operators, but they're the unprotected operators higher up, and those surely can have complicated operator dimensions.
Okay, maybe we can discuss this